I'm coming here from San Francisco. I was in the neighborhood. I was at a conference in Budapest, so I thought I'd come up to Kraków and say hello. But I'm leaving on Thursday, so unfortunately I don't get to explore a lot of the city, but I thought I'd at least meet the local Erlangers and give a talk. So today I'm going to be talking about random choice and just randomized algorithms in general. And why this topic? Well, I've written an ad server in Erlang, and randomized algorithms are very useful for ad serving. And they have some other interesting applications as well. And so a little bit about Erlang's random module. I mean, you all are Erlangers, so you might know a little bit about this. But the algorithm used by the random module in Erlang is very, very old. It's designed for 16-bit computers, and it's not really a very good random algorithm. We've done much better since the 70s, or whenever that algorithm, or the 1982, sorry. And it has poor results, and you probably shouldn't use it. But because it has a nice mutable interface with side effects, it works well for slides. But if you are actually doing real work with random numbers in Erlang, you should consider using either the crypto module or perhaps a third-party library like SFMT Erlang, which implements the Mersenne twister algorithm, which is commonly used with other programming languages such as Python. So one of the simplest applications of random numbers is to simulate a fair coin. So you flip a coin half the time, roughly, heads, half the time tails. And to simulate that with the uniform function in the random module, you simply call it heads when you get a result less than 0.5 and tails otherwise. And so here's just a little simulation of what it looks like to flip a fair coin. And so we're getting numbers between 0 and 1. And if it's less than 0.5, we consider it heads and color it white, and otherwise it's black. And you can see that it's not perfectly fair. We've flipped it 13 times, and 8 times heads and 5 times tails. And that's expected. If there aren't some aberrations sometimes, your algorithm probably isn't truly random. And so another common thing to do with a random number generator is to simulate a roll of a dice, or choosing an integer between 1 and n. And this is very easy to implement with the uniform function. You simply add 1 and multiply by n and truncate it. But Erlang implements this in its own library, so you don't actually have to implement it. You just call uniform with one argument. And this is very similar to the simulation of flipping a coin, but when you flip a die, there's 6 possible choices. As you can see, it's not perfectly balanced, but that is expected and totally okay. If I did this enough times, it would look very similar. Okay, I was a little worried there might have been a bug there because I didn't see any 6s, but it's okay. So when you have these algorithms to generate random numbers, you can start doing more interesting things with it. One algorithm is called random selection without replacement. And so what that means is you randomly choose an element from your set, and then for the next iteration, that element is no longer in the set. So you can use this kind of algorithm to simulate shuffling a deck of cards, or a list, or perhaps choosing a name from a hat for a raffle. And implementing this in Erlang with the random module is very simple. You simply give the list as input, and you pick a random number uniformly for the index of the list. You split the list, and then you combine the beginning of the list before the choice, and then the list after the choice. And of course, if you pass in an empty list, this will explode, because you can't choose an element from an empty list. And here's a simple simulation of what random selection without replacement looks like. So we picked the last one. Okay, that doesn't look very random, but it should be. See, there we go. And you see at the end here, we're out of elements to choose. I decided instead of blowing up this implementation would simply start over with the list that we had shuffled. So this kind of algorithm is commonly used with games or any other situation where you don't want the source list to remain the same. And so to get a little more complicated, more real world, the weights when you're choosing are not always uniform. So you have some selections that you want to happen more often than other selections. Some examples for this would be unfair dice or perhaps ad selection. So in ad selection, weighting is very important because some ads are worth a lot of money and some ads are worth almost no money. So you want the ads worth a lot of money to show up more often, but you still want to give the other ads a chance. Or also if you're simulating a sporting event, for example, you expect one team to win more often than another team, so you weight the selection. And so implementing this gets a little more complicated. Here's a very simple implementation. It's not extremely efficient, but we maintain a counter for the total sum of the weights in the list. And then for each element in the list, we have a key, which is whatever identifier we use, and then we have the weight for that key. And so and here I didn't have room on the slide to actually choose the n, but we choose n as a uniform random number between 1 and the sum of weight. And to select it, we simply iterate through the list, subtracting the weight from n until n is less than 0. And when n is less than 0, then we take the new sum, and the new sum, or we take the key that we found, and we take the sum minus the weight of that key, and then we combine the accumulator with the rest of the list. But because it's Erlang and we build the accumulator back to front, we have to reverse it so that the list is in the order that we started. And so another common algorithm is to do random selection with replacement. So this is a little easier to implement because choosing an element from the list doesn't change the list. And this is similar to just rolling a die. You have a list between 1 and 6, and then you do random selection without replacement, and it's equivalent. So because it's simpler, the algorithm is much simpler. We just choose a number based on the index of the list, and call list m, and that's it. And here's a simulation of that. Basically the same sort of thing, except the original list doesn't change. And in order to make this selection weighted, we have some options. Some are very simple. The simplest option is just to add the item to the list multiple times. So in this case, we want A to be chosen about half the time, and B, C, and D to be chosen about 1/6 the time. So to implement this very simply, we put A in the list 3 times, and the other elements go in the list once. And that looks something like this. So the asterisks get chosen a little more frequently because they're chosen about half the time. And the naive solution here uses a lot of memory because you have to have a list cell for each time that it's in there, and the list gets larger as the weight distribution changes. You have problems where you have to put it in a lot more times than you would want to because of the way that the numbers divide into each other. But you can do much better by counting each unique choice. So the trade-off here is that it's harder to seek to the nth choice, but you can see that we only have to occupy 1 cell per unique element in the list. And you can do even better than that. There's a very interesting algorithm called the Alias method. And so how the Alias method works is you create n virtual coins, 1 for each unique choice. So in this case, we had A, B, C, and D. So we have 4 virtual coins. And now to choose a coin to flip, we first roll a die. So that die has 4 sides on it. And then after we roll the die, then we flip the coin. So to choose from any number of sets with any weighting whatsoever, we only have to roll 2 random numbers. We roll a die and then we flip a coin. So we have 0-1 selection. regardless of how big the list is or how the weights are distributed. And it also only uses ON memory. We only need one cell for each distinct element in the list. And there's a very interesting algorithm that allows you to initialize it in linear time as well. But unfortunately, the algorithm here doesn't fit on the slide. But if you want to look into it, it's called the Bose alias method. And here's a simulation of what that looks like. So in this case, we have 4 coins. There's the coin for A. So if we choose A happens 100% of the time. If we choose the coin for B, 2/3 of the time we choose B, otherwise 1/3 of the time we choose A. And you see if you add all the numbers up, A happens half the time, B, C, and D happen 1/6 of the time. So here we rolled the die, we got 1, and then it doesn't really matter what coin we flip because 100% of the time it's A. And here we rolled a 4, and then we got a value less than 2/3, so we chose D. And so this is a very efficient algorithm for choosing a weighted selection without replacement, or with replacement, sorry. And so the reason I was looking into these different algorithms was, 1, for the ad server, but 2, we had an IRC bot that would randomly say stuff. And it turns out that if you implement this poorly and you put a lot of text into this IRC bot, then it becomes very slow. The initial version of this bot actually ended up using so much memory it couldn't run anymore. And if you use this very clever algorithm where you reduce the amount of memory used and you make the choices very fast, unfortunately it's very expensive to update because you have to update the entire list every time. And so if enough different words are said, then it's very expensive to say more words, or even just to update the counts of existing words because you have to update this entire list, especially in Erlang, where it's a purely functional data structure. And there's no sharing at all because all of these distributions are changing by way of the method that you use to build this data structure. So this is actually a pretty difficult problem to solve with Erlang's purely functional data structures. So one possible solution would be to use a tree. Like you have GB trees or the dict module or something like that. And this gives you pretty fast log n updates. And you generate log n garbage because there's good sharing between versions of this tree. But the problem, or a potential problem, is that seeks get a lot slower because you have to essentially seek through the whole tree in order to find the weight that you're looking for, because you organize the tree by key to make updates efficient. So another potential data structure that I found to be a pretty good compromise between speed and memory was to simply use a sorted list. And so the way that you make this relatively efficient is you put the highest weighted elements first in the list. And the nice thing here is you generate less garbage because the highest weighted elements are more likely to get updated again because they happened often in the past, so they're likely to also happen often in the future. So updates don't generally create a lot of garbage. And like the tree solution, there's a worst case ON for every operation, but it has a very good amortized common case because all of the big numbers are up front and you're more likely to choose that. And so what I have here is I have a database full of words. Okay, so here's a Edsger Dijkstra quote. They were mostly Americans and talked with the self-assurance that we tend to connect with competence. And so in this distribution here, we see the word wit occurs twice. So if we start choosing words here, it doesn't make any sense. But if we add more words, then we can see that when we choose from that list, it should often choose towards the top. So in the top here, we have the top 10 elements, and if it gets below there, then you'll see the bottom of the table. And if we add a whole bunch of quotes, then this text makes even less sense, because we're really just seeing the most common words. There's no structure at all. In order to make text that makes a little more sense, you can use a technique called Markov Chains, where you represent the words as a finite state space. And the interesting thing about Markov Chains is that present, future, and past states are independent. You only have to store what the current state is. And so you represent a Markov chain as a graph where the edges represent the probability for state change. So with text, we simply have a node in the graph for each word that was said, and then the edges represent when that word was said after the previous word. And in the implementation of this, in order to have it generate sentences, you simply use a special token for start and stop. In this JavaScript case, I used an empty string for the start token and some other string for the stop token. And you build a weighted random selection data structure per word. So it's simply applying the data structure that we built before. We're applying it n times in order to build this Markov chain. And so here's what that looks like. So we'll add a quote to the database with just one quote. So we see the word with happens twice there, and that's the only choice point in that graph. Otherwise, the word where only comes after they. So when we generate something from this graph, we have they 100% of the time, were happens after that, 100% of the time after were, the word mostly happens. But we can see something a little strange happened here. It didn't copy the entire sentence, because when it got to the word with, 50% of the time the word the happens next, and 50% of the time the word competence happens next. So we got a shorter sentence here. But as you can see, it is actually even correct English in this case, which was a lot better than just choosing random words. Okay, so here it was able to generate the original sentence. And here it actually generated the same phrase twice, because it simply chose the word the again. And it can generate arbitrarily large text like this, but it's very unlikely to do that. And so if you start adding more quotes here, then the words make a little less sense. But it produced a sentence that kind of makes sense. Programs, even the self-assurance that we tend to connect with competence. It's not a lot of sense, but it still looks like English. And that's really the task, is we build a data structure that represents the probabilities of words that happen next to each other in English.
Can you submit paper with that? Some random graphs.
Oh, people have actually done this, I think. And I think maybe once or twice a paper has been accepted when generated using this technique.
Should be some prize for that.
And if we go ahead and add a whole bunch of quotes here, we hopefully will see something a little more interesting. With all higher level programming languages, that kind of Boolean as education proof at the computing community displays a criminal offense. It is right, software engineer. So you can kind of generate like poetry almost. And although in this case it doesn't serve a useful purpose, it provides quite a bit of entertainment. Focus, no. All right, so that's pretty much all I have today. But the slides are published online, and the source is at GitHub. And if you have any questions, you can ask them to me right now, or feel free to email me or send me a tweet. Thank you.
Did you have a need for like you need randomness, but only to a certain extent? Like at some point you want to force some values out of the system because of the randomness that they were never chosen, and sometimes it's desired to behave like this. And did you ever try to do something like that?
Sure. So in our ad server, there were certain decisions that we wanted to be made 100% of the time. Usually this would be the exclusion of showing an ad. Like say you've seen an ad too many times, we don't want to show that ad to you. Or you're in the wrong country to display that ad. And we simply filtered the data set before running the randomized algorithm in those cases. The most important reason that we used these randomized algorithms is that no coordination was necessary. So we have all of these ad servers making decisions completely independently from the decisions other ad servers were making. Because we could choose randomly. It didn't have to be in some specific sequence, because otherwise maybe one request they would hit one ad server, maybe some other request they would hit a different ad server.
Okay, because I read that especially with random game algorithms, you want the behavior that increases the chance of some event to happen after time. So I know you have a chance of backstabbing or something, and you have 20% of doing that, but after, I know, 10 tries, it will always happen, because it's more playable that way.
Sure. So we had, in our ad server, it kind of worked the other way. Basically, you would have an ad that had a very high weight, and then you saw that ad, and then the weight would be exponentially less, or logarithmically less. So then the more times you saw that ad, the probability for seeing that ad again would eventually go to 0. So if you wanted to simulate the other case, you can simply use a number so large that it is completely improbable for anything else to be chosen. That would be one way to simulate it. Another way would be to simply have, say, a case statement that if it happened 10 times, then do this. I don't know if there's like a general solution to that problem.
Okay, could you talk a little bit about those two other modules that are available in comparison to the standard random module, the standard random function call?
Okay, so I talked about 3 modules. The first module was the random module, obviously. The second module was the crypto module. The crypto module ships with Erlang. The advantage is that you can get cryptographically secure random numbers. The disadvantage is that cryptographically secure random numbers are much slower to generate than pseudo-random numbers without so much entropy. The other module I talked about was SFMT-Erlang, which is available on GitHub. And if you go to the slides, there's a link to it on that slide, or you can just search for SFMT-Erlang. And so that's an implementation of the Mersenne twister algorithm, which is simply a much more modern algorithm to generate random numbers. I think it's from maybe the late 90s. And it works with, I believe the SFMT algorithm might use 64-bit integers, which allows it to much more efficiently utilize today's computers and generate, actually more than 64 bits of randomness at a time, whereas the random module would do 16 bits at a time because it was designed for 16-bit computers.
Sure.
with 32-bit floats, essentially.
And there are, just as a concern, there are C implemented or there are Erlang-based implementations in those two modules?
So in the crypto module, it's all implemented in C because it's really just calling OpenSSL.
Okay.
In the SFMT Erlang module, I believe that they have two implementations. They have a much slower one implemented in pure Erlang, and they have another one that's implemented as, I think, a NIF. But I think it's pretty well tested. It's been out there for a few years, so I would be pretty comfortable using it in production.
So do you know what happened to the approach that Kenji Rikitake? He came up with an idea of changing the interface to the existing random module to accept like five number seed. I think that's the algorithm you are talking about, 64-bit precision seed based. They were discussing it to introduce it to the original Erlang mainstream. Do you know what happened to that?
I do not know. I wasn't closely following that
I
discussion.
know a lot of people were pointing out that the current implementation is pretty weak and doesn't give you much randomness.
Yeah,
So,
yeah. The current implementation is very weak. I mean, if you generate a seed that has zeros in it, then it's very, very weak. And mostly people generate the seed using
Now.
Erlang now, which can very easily have a zero in it somewhere. So it is really a poor choice, but you know it's there.
It works.
Yeah. But I believe Richard O'Keefe had a lot to say about that at some point.
That's not every other one.
Was the Erlang implementation of these algorithms even at any point a bottleneck for you, or?
In our ad server, we were actually using the crypto random number generator, and it was not a bottleneck. So for most applications, you shouldn't expect to have a bottleneck in your random number generator, especially if you're using a good algorithm. Like for all of these examples, in order to choose an element from the set, you would generate one random number. There are other randomized algorithms where the speed of generating a random number is a lot more important. For example, there are some sampling algorithms where you have a data set, a stream of data, and you don't even know how large the stream is. And so each time you receive an element from that stream, you have to generate a random number to decide whether you sample that element or not. So you build like a bucket of however many elements you want to keep, and you can, without knowing the size of the list, and without choosing all of the elements from that list, you can have this bucket of samples. But for those algorithms, it's very important because you're choosing a random number for every single stream element that you process. So in those cases, it would be a lot more important. You might find that in like a performance metrics library. Like if you wanted to see what the median request time was, then you might use an algorithm like this because you don't know how many requests you'll have.
I think most of that mathematical functions are implemented as hype backend. I think that's what Folsom uses as a backend for like selecting percentiles or means or medians.
Yeah, I mean that's would certainly help a pure Erlang solution, but I haven't done any benchmarking. Any other questions? It doesn't have to be about this. I'm happy to talk about anything.
So regarding your ad server, does it have any the most expensive part of it, or
So the most expensive part is that the ad server participates in several ad exchanges. So for a given request, we're sending out multiple HTTP requests to third parties.
DSPs?
To what?
No.
Yeah, in many cases that is the biggest bottleneck. In some cases we have an ad in our own inventory that we can choose without any third-party requests, but in the cases where we make a third-party request, that is most certainly the bottleneck. Other bottlenecks in the past have been memory, for example, because we put the entire database of potential ads all in memory so that we could choose from it very quickly. And we ended up working around that by taking this data structure and compiling it to a Beam file and loading it as a module. This allowed us to represent it in a data structure that would be shared across all processes, because as a single gen server, it's a bottleneck, but if we don't need a gen server at all, like any process can speak to this data structure with no copying, then we eliminated the bottleneck. So that's why we ended up compiling it to a Beam file, because the data structures that are constants in modules are shared. It's basically reference counted, because processes in Erlang maintain references to the modules, the versions of the modules that they refer to. So it's able to use data structures from those modules without any copying at all.
Is it read-only or?
Well, it's read-only until we load a new version of the module. So we modify it infrequently.
Okay. Why don't you can just use ETS tables?
You can use ETS tables, but ETS tables require copying in order to do anything.
Oh yeah.
So it generates a lot of garbage. Like, say for example, in a given ad request, we might consider hundreds or thousands of ads, and then that would all become garbage that would need to be copied and then collected. But we have tried solutions with that. It might be possible to more cleverly use ETS, but this kind of selection, the kind that we were doing, it proved to be difficult, because the weight of an ad is different for each user based on the ads that they've seen in the past, so we can't simply store them in some fixed order. We have to walk most of the data structure most of the time, at least within the countries that are relevant to them. I guess that's it.